So let's consider the following example. So what I want to do is, here's our first example, just as a little bit of a warm-up here today. Last time I went through things like polynomials, we talked a little bit about, we'd seen actually some interesting examples, but I thought I would show you something that actually kind of connects nicely, say if you need other kinds of exponents for your big O result. So for all integers k greater or equal to 0, and suppose I give you a real constant, epsilon. So you can think of epsilon as any real constant that is greater than 0. So this means it can be very small. It could be like 0.1. It could be like 1. It could be 10,000. Whatever you like, as long as it's some real number that's bigger than 0. But it's a constant here. Then we're going to say, so the claim that we're going to prove is that n to the power of k is big O of n to the power of k plus epsilon. Now you might ask, Dan, why would I need this information? Well, like you'd be like, oh, well, look, it's clear, it's obvious to me. I'm just using these words deliberately to talk about, okay, reasoning here. Okay, it's obvious that this k is not it's not going to dominate over, I'm just using kind of loose terminology here, over k plus epsilon because epsilon's greater than 0. That's true, right? But the thing is, we need to actually have some way to check this. And I'll give you an interesting application of this claim in a moment. So let's prove this claim. And it's actually surprisingly simple. Remember, we come back to our game plan. We're going to figure out those two constants, right? Because that's what's in the definition, right? It says we have to find these two constants, c and n0. We have to find them, but I also have to reason out like why they work, right? I can't just give them to you and just say, oh yeah, just deal with it. They just exist. If I'm doing a formal proof, that isn't sufficient. So I'm going to say we find constants. Constant c. So remember, c is a positive real number. And n0, which is a positive integer. So that for all n greater or equal to n0, it has to be, well, I'm just going to plug in my two functions. Remember, this is f, that's g here, so that's f, n to the k, and n to the k plus epsilon is g. So it means that n to the k is less than or equal to c times n to the k plus epsilon. Now, we're going to use that approach that we had last day. I called it the lookalike approach. And you'll notice very quickly that we have n to the k on that one side, on the left-hand side. To mimic this on the right-hand side, notice that k is in fact present in the exponent and epsilon is in fact greater than 0. So we're going to use that intuition we talked about where we said it was kind of obvious. So we're going to just use that intuition to help us. But we need to pin it down, okay? So notice that if I just make c1, then it's n to the power k is less or equal to n to the power k plus a little bit in the exponent. So if we go with that, it seems pretty nice. So I'm just going to make an observation first before I pick it, and then everything will flow a lot nicer, okay? For all n greater or equal to 1, observe that when we divide both sides of the inequality, both sides of the inequality, we're talking about this one right here, by n to the power of k, we get the following. And keep in mind, this is a legal step, so let's just proceed. Well, it says that n to the power of k divided by n to the power of k is less than or equal to c times n to the power of k plus epsilon over n to the power of k. Well, if you look at this right-hand side, if you remember properties of exponents, and keep in mind, I will do at some point some coverage of this, is that if you have n to the power k plus epsilon divided by n to the power k, notice the bases of these exponents are the same. So it's actually, instead of it being where, like, if you just look at this, like, okay, what do we do with that? We subtract the exponent. So I have k plus epsilon subtracting k, and it means I end up with just epsilon. So I end up with c times n to the epsilon, which if I rewrite this inequality now, this is actually me saying, because remember, n to the power k divided by n to the power k, this is just 1, right? So we have c times n to the power of epsilon is greater or equal to 1. So you can see quite quickly once I've done this, or at least my hope is that we just need to now figure out the constant. Well, the great thing about this is that we're going to pull out a property that we know about n to the power of epsilon. It's a polynomial, but it isn't necessary that it has an integral exponent, meaning it's not integer valued. It may be real valued, as we have epsilon being a real number. But remember, epsilon is positive. We're going to pick c is equal to 1. Then we need to find n0, so that n to the power of epsilon is greater or equal to 1 for all n greater or equal to n0. Well, here's the great part. Well, if you look at n to the, like, if you have a background in calculus, you'd look if you look at n to the epsilon, you would know right away, if you calculate the derivative of n to the power of epsilon, you could see that this, in fact, the derivative of n to the epsilon, it will be something that is strictly positive. And if you know this fact, then you know the function is increasing. It's an increasing function. So that means that if I plug in, say, n is equal to 1, notice I have 1 to the epsilon. Well, 1 to the epsilon, well, 1 to the anything that where the exponent is greater than 0, it's just 1, right? So that means that if it's an increasing function and 1 to the epsilon is equal to 1, that means that, well, that means that it's never going to get smaller than 1 on that this right-hand side is always going to be bounded. So notice I have c to the n to the epsilon. Well, if this is going to be increasing, so n to the epsilon is always going to be increasing regardless of what epsilon is. And I know that when I put in 1, so it means if I go 2 to the epsilon, 3 to the epsilon, I know it's always going to be the case that it's going to be, this function's value is going to increase, okay? So we're going to use that fact to help us conclude this proof, okay? So observe that n to the epsilon is greater or equal to 1 for all n greater or equal to 1. Now, if you need more explanation here, you just say that n to the epsilon is an increasing function and 1 to the epsilon is equal to 1. So I would recommend, if you need more detail, I would suggest strongly you put that right here. In my notes, in fact, I make a note of this. But I'm sort of running out of space here. So select n0's. Oh man. Select n0 is equal to 1. Then now we could just conclude, because now we can just use the definition of big O. Therefore, by the definition of big O, then we could say n to the power of k is big O of n to the power of k plus epsilon. And that concludes the proof. I'm just going to write that box there to say that we're done the proof.